Just to finish off lecture 8 with one final example. Name 3 laser welding modes which the melt pool can take: conductive, transition, and keyhole mode. What determines transition between one mode and another? So it's mainly the laser power density. So if that laser power density is sufficient that your depth of the melt pool is greater than, so the aspect ratio of your depth, width to depth is above 1, then you can say that the keyhole has become the melt mode has become a keyhole mode. So physically what's happening, as I explained earlier, was that we're starting with starts with a vaporization. There's a plasma that forms on top of the melt. That plasma basically re-radiates the thermal energy back into the melt pool, and that acts to accelerate the process, by which there's almost like a boring into the material, which is why you end up with these classic tooth-shaped melt pools and heat-affected zones. Right. So what we're going to go through now is aspects of process control. So I've shown you what the parameters were, what's underlying the different parameters, what effect they have down at quite a fundamental level, the interaction between the laser and the powder. So what we're going to link up now is some process control maps and the defects, which are the main defects, which are form additive. So these are porosity, residual stress, geometrical shrinkage. We're going to look at the effect of these defects on the properties. We're going to go individually into the porosity, residual stress, geometrical effects, delamination, surface roughness, but how do we control them is through potentially through process maps. So if the main defects that we have in AM, and here I have to put a disclaimer in, because these defects are not anything that you wouldn't find in any manufacturing process, whether that's investment casting, die casting, in plastics, injection molding. So they're typical of where you have a molten material which solidifies. So porosity is not inherently an additive manufacturing problem. Neither is residual stress, so you get high residual stresses with lots of other types of manufacturing process, and they have to be taken into account when you design a component. Geometrical shrinkage, you get in casting all the time. Toppling, sinking. Surface roughness is not inherently an additive manufacturing problem, but it is one which we have to take into account. There is quite a bit of variability on surface roughness. The stepped geometries results in higher levels of surface roughness, which is typically, if you make a surface which is at a given angle, then inherently it's a digital process, so you're doing it on a layer by layer basis. You're going to have 50 micron steps, and that's going to give you a level of surface roughness which will kind of dictate what your eventual surface roughness will be. The angle at which you do that is going to affect the surface roughness. But all of these defects, they show themselves up, and they show themselves up in the properties. And with any process like additive, which is new, those properties aren't necessarily what the end user is going to make the component is actually looking for in a functional component. So that inherent step geometry or digitalization of the layers results in a very low free surface roughness. Because of the high cooling rates and also the porosity being distributed across a plane and also through the build volume, we'll end up with non-isotropic material properties. And typically, whether it's in aerospace, in engine, or any critical components which are under high temperature, the last thing you want to have is variable or non-isotropic material properties. We do end up with the scatter material properties universally, so our tensile strength can have a level of scatter, which is linked to the anisotropy. When you have porosity, that does reduce your fatigue and creep by strength of the components. It may reduce the high temperature strength and its also its ability to withstand corrosion. But again, this is not always inherently just a problem about it if this is across other manufacturing processes as well, particularly net shape processes. So, what is porosity? Well, it's the absence, it's a void, not necessarily filled with gas, it could be filled with gas. It may happen for various reasons. What we want to know is how do we control that porosity, how do we minimize that porosity to have the highest density possible. What we want to know is how it comes about in our parts, in the powder bed, or selected laser melting, how can we control it, and what is an acceptable level of porosity for any application. And that's like asking how long is a piece of string, because different applications have different acceptabilities and different porosities. So we come to our first process map, which is where we've mapped laser speed and laser power, which are two of the typical parameters that you will see associated with powder bed laser melting, or even electron beam, or any of the welding processes. And you can see here that they've mapped out porosity as a function of laser speed and laser power. Right, so this takes a pretty typical layout. You'll have, if your laser power is not powerful enough, it doesn't matter what speed you're going at, you're going to have, if no consolidation of the powder or lots of porosity. Then as you slow your laser speed down, but you increase your power, you're going to have an area fully dense. So it goes from fully dense to not consolidated at all. And then there'll be a range of areas which you might be interested in trying to find an optimal location of speed and power. So another example here from Kruth shows again that variation. This time what they've done is they've taken laser speed or scan speed, and they've played around with the hatching space. And you can see that there are various resulting levels of porosity. So a larger hatch space and higher speed, you get more porosity, as you would expect, and less porosity down in the lower hatch spacing and lower scan speed. So some of these things can be very logical. You have to think about it very much to see that it makes sense. Again, another example where you might be comparing hatch pattern with porosity. So this is, again, coming back to this study that we did earlier, quite a long time ago now, 3 years ago, but it's a very simple study where we just played around with the point distance and exposure time. And we came up with a series of printed metal cubes, all in 316 steel. We did multiple repetitions of the same thing. I showed you earlier how to calculate the energy density in joules per cubic millimeter. So that's exactly what we did for each of these different settings. So with everything else kept constant, just changing the point distance and the exposure time, we end up with this color map. Color map represents low energy density, which was exactly what we calculated last time on example 8.2. We worked out 19 joules per cubic millimeter. And then here, where you have a longer exposure time and a shorter point distance, the point distance is short enough now, you get a lot of overlap, and you're putting a lot of laser power in the same spot. That's our red. This is the highest energy density that we've had within this particular design of experiment. And between that, then we have a range. Now, I also showed you this earlier, and I think hopefully now you'll understand a bit better how we actually work out what the energy density is along the bottom axis there. That's our laser energy density, and we've got relative density, now density of the material, which is based upon various ways that we've measured this. You guys have done some of this in the labs. We've done, you can use Archimedes, you can try to measure it, get the volume, get the weight, get the density, or you can also use a microscope, where you actually look at enough cross-sectional areas down the microscope, and you use image analysis then to pick up on porosity and the relative density related to the porosity. And you can see there that as we go through the, on the lower energy density, we can see a lot of porosity. you can still see clearly the hatch pattern. You can see the lines going up, coming back down. In that one C12, I'm going to show you in a minute, you can see very clear indications of what the path was. You can see unmelted powder, big pores, and as you increase that energy density, you can still see some. You can see the ghost lines of the tracks start to close until we have a much reduced porosity. Then after a certain point, we've actually started to overcook the material. We put too much energy density into it. And what happens then, and this is just a hypothesis at the moment, we haven't proved it, but we think it's the case, is then you get more keyhole mode melting going on. And then when you prepare the material, and you're sanding it, and you polish it back, the porosity, which is inside those keyhole weld profiles, gets ripped out, and it leaves this kind of more circular type porosity at the end. So let's just step through those quickly. Here you see C12, that relatively low energy density. You can see very large porosity. We go up in the energy density of the laser. The pores start to close a bit more. By 70 joules per cubic millimeter now we've got a much lower amount of porosity, which is roughly about 2%. And then we have what we would call the optimal density, the highest, most consolidated part, the lowest porosity, around about 99%. And this corresponds to about 120 joules per cubic millimeter. After that, we keep on putting in the laser energy goes up, and we start to see this other form of porosity start to turn up. So this is quite typical of the effect on density. So you can look up Knauf from 2014, and also clear there, but if we look at the next page, it's the same thing. They tried higher speeds and higher power laser to do this, about 400 watts at the time. And again, you see this kind of almost quadratic increase in these graphs, different laser powers. But you see that there is an optimal. And once you go beyond that optimal, you start to actually reduce the density. So I've shown you already as well, this is in essence the beginning of the process map. And again, it's playing with two parameters here, the power and the exposure time. So just generally taking on the overview, this is for a DMLS, direct melting of laser sintering steel. So regardless of whether you're using electron beam process, or laser sintering, or laser melting, this is the kind of process you build up. And you have these different zones, which are typically, it hasn't touched the sides, the grey one there, and it's unconsolidated. You have some sort of intermediate zone where you have a lot of breakup of the tracks, and then you have a very high, the higher density, better melt tracks forming in what is zone 4 on that particular map there. And you might have this yellow highlighted map, which is not necessarily the best one you're looking for, but it's somewhere there is the optimal. How do we build up the maps? Well, here's another example. This is a CO2 laser with steel powder. So lower laser powers, but potentially a wider beam area. So you might actually just look at the powder track, the melt tracks themselves. You can see the breakup. These guys have classified it under different zones A, B, C, D, and E. Looking at the melt tracks, you can see B has quite a nice sort of U shape to the track, whereas the other ones are broken up, more delicate, less delicate, or even unformed altogether. And you can see what they will do. They'll typically cross-section some of the tracks and put them under it, show them up on here, and it will show that there are some tracks that haven't formed very well at all. These might be too small. Here you've got some area around about where the bead is there, that you've got the sort of shape of melt bead that you actually want to be retaining throughout the whole of the build. Again, it takes a lot of points, takes a lot of time to do this kind of building up of process maps. And one thing you can see there, that although there's a lot of similarity between process maps, the variation of the type of laser, the spot size of the laser, the speed at which it's done, the machine it's done on, all of these things are very different, and that's one of the problems that is there with additive manufacturing at the moment. There's a lot of variation in the systems that are being used, and one process map doesn't just cut and paste and go on to the other one. There's no generalized process map. And that's one of the problems, really, with being able to just, you would hope you'd be able to take a material that works with one machine and put it in the other, and it's not necessarily going to work the same way. So here we see for the steel power the very clear differentiation into 1, 2, 3, 4, 5, 6 different zones. And again, these are all determined by looking at the formation of the melt bead. Just to show that that variation with different materials and different lasers, but essentially doing a very similar thing. We're looking at the effect of varying the power and the effect of varying the speed, and what happens to the melt tracks or the consolidation. So if we just focus on these, on this one here for the time being, which is probably the most complete, we'll have, let's start at the worst area where we might have very high speed and very low power. Okay, so basically we haven't got enough power density and the density of the laser to be able to melt the powder, so there's no consolidation. As we increase the power on that same speed range, we will actually have some melt tracks, but they might be very fragile. So in this zone D, they are more regular, but they might be frequently broken up. And if we remember back to that, the last lecture, I showed a picture of what looked like the plateau Rayleigh breakup into ball. So this could be happening here. Things generally get better when we go from C into B. We're getting enough. We're moving slower. We're putting more power into it, so we're able to get longer, unbroken lines of solidified tracks. But we've also got this area A, where we might put too much power into it for that particular speed. So what we know is that somewhere around here is going to be the optimal power-speed ratio, or power-speed combination that we want in order for our builds. And I think this is shown quite clearly if we're looking to consolidate our tracks using that kind of profile. That's where we want to be. We don't want to overcook it, where you get potentially vaporization and too much power, and it just basically blows the track apart. You get these very odd shapes, or down here altogether, where you get very few or very delicate melt tracks together. So that's where we're heading to go, we're trying to get to. I've already kind of put the idea into your heads that the speed at which something is moving at a given power is important in terms of the length of the melt ball. The length of the melt ball to the width of the melt ball might determine whether there's going to be balling happening, which could be part of that. An effect where you actually get the opposite effect, your final density is affected. But the other instability that is a little bit more controversial is whether or not keyholing is taking place altogether. There is some evidence that, and this shows it quite clearly, that as you vary your power, you vary your scan speed, that you end up typically with areas where you might want to be melting and moving at. So here we have some sort of nice melt tracks, but potentially after a certain point and with low enough speed, we enter into keyhole mode melting. As I mentioned earlier, it is thought that we want to stay away from keyhole melting in the powder bed. Not all processes want to stay away from keyhole melting, so there are some laser welding where you're putting two materials together where you actually want to have that penetration on a large scale, and it acts almost like a staple. So keyholing is not always bad, but in this case it's not necessarily thought to be particularly good. So, what we did talk about a little bit last time, we didn't do much about it, though, was actually trying to quantify the transition between conductive and keyhole mode. I said that there were various ways in which we can categorize the amount of energy that's coming in through the laser. I mentioned energy density, which is the one we've actually calculated for our systems, but you can also use power density, or you can also use normalized enthalpy, which sounds very complicated, but it's actually just another way of maybe adding some material properties into a similar equation that allows you to quantify how much energy is coming in. So here are some examples. Here we've got for a continuous laser which has a 1.1 or 1.2 mil diameter, and we've got various power densities for that, an interaction time of 10 milliseconds. And we can see the penetration depth. So if you think that 1.2 mil is roughly there, you can see that once it's gone up to about 1.2 mil in this area, you're pretty much going to have keyhole mode. There is a transition as it goes through. So this is work done by Cranfield. And I think this was done on a solid, not a powder material. The one at the bottom here was done on a powder material, and you've seen this before. And these guys use the normalized enthalpy way of essentially you're getting your power density here. And this y-axis is the depth of the nutball divided by the beam width. So once we go above 1, you see there, you start to get all the black points. We've gone into a keyhole mode. And they say, indeed, that if your ratio, if your normalized enthalpy is above 6, there, sorry, if your normalized enthalpy on the x-axis is above 6, you're going to be starting to get transitioning into keyhole melting. So, what we are doing here at Swansea is looking at a way of generalizing process maps where we simulate the process map, which allows us to use material properties and thermal equations and some modifications to do with the transition into keyhole mode. And you guys are working on this at the moment, a couple of your projects. You're using that code. And what we're saying is that with that code and the material properties you've got, you can start to build up a process map right through simulation. So the usual laser speed on the bottom, laser power on the y-axis. So we get a colouring according to the normalized enthalpy, which shows us that, and these contour lines here are normalized enthalpy. If it's above 6, you're going to be heading into keyhole area. But what we can also get from the model is we can get the length of the melt pool. So we can also start to rule out areas where there might be longitudinal instabilities based upon quite a simple criteria of the melt pool length. And that, surprisingly, comes that when you actually work out your optimal location of power and speed, it actually puts you slap bang in the middle of where we would normally be working with anyway with our lasers. So speeds in the region of about 500 millimeters per second, powers in the region of 180 to 200 watts. So that's what you guys have got in your project, and I thought the results were quite surprisingly pleasing for a change. here's an example, and I'm only going to run through 2 examples now, and then we'll stop and carry on next week. First example is just to read off some values from the graph. So, a fiber laser is focused on mild steel. This is given the power, power density. Is PD is given by power divided by the area. Where A is pi r squared is the area of the laser beam, R is the radius of the beam. If we divide the interaction time as T equals R over 2U, where U is the speed of the laser, we have to determine from figure 5 which mode the weld is in when we have a laser power of 1000 and a diameter of 0.04. A laser power of 4000 watts when the diameter is 0.15, and a laser power of 2000 watts when the diameter is 0.2 centimeters, and U is 20 centimeters per second. So first of all, we need to check that the interaction time is 10 milliseconds. All right, so if you put that into your into the interaction time equation, just divide the radius by twice the velocity. So first of all, we need to check that the interaction time is 10 milliseconds. All right, so if you put that into your into the interaction time equation, just divide the radius by twice the velocity. All of those ones should work out that the interaction time is indeed 10 millimeters per second. I hope. That's something for you to check later on. But let's assume that they are. Okay? So the first thing is, let's put the laser power 1000 watts, that diameter and that velocity. So we put power, diameter, work out the area, just check our velocity is in there. Then we can work out the watts per centimeter squared from those two. Convert that into kilowatts per centimeter squared, and convert that into megawatts per centimeter squared. So once we have the megawatts per centimeter squared, that gives us our power density. We come on the power density curve, and we can see immediately that for the first one, which is this combination here, we have a power density of 0.79. 0.79 would put us somewhere in that region up there. So we would be in the keyhole mode of melting. For the second one, we follow through, 0.22 would put us in this region here, so we're in transition mode. And with this last combination, we would have a 0.063, which would be down in this region here, so we would have a conductive mode of melting. I've only just got that example ready for you guys, so have a look at it. When I meant to upload it last week, but now you're here, I'll upload it tonight, and see if I made any mistakes. Right, this is a bit more involved. What we're going to do now is just to use the normalized enthalpy equation, which is just, think of this as an indicator of how much energy is being put in by the laser. Okay, so we're given a set of a laser with a spot size of certain power. We're given some properties that we're going to put into the equation. Then we're told let's pick a 300 watt and a line speed of 500 and work out where we are on this graph and whether or not we think what mode of melting would we be in under that. So that's the equation we're given. All we need to know is the left-hand side is normalized enthalpy. And the right-hand side has all the numbers, all the variables in here are given to us. A is the absorbability of the material. B is the power. S is the normalized enthalpy of melting. Pi is pi. D is diffusivity. U is the velocity. And sigma is the diameter of the beam. Okay? So we're given AD and sigma, where we have to work out what the enthalpy at melting is. So we simply use this equation which I gave before. Density times specific heat capacity times the melting at the temperature point. Density 7,890, count steel. Specific heat capacity of 300 joules per kilogram Kelvin. And then the temperature in Kelvin, 1,650. Gives us a, this should be joules per kilogram, sorry. I told you I'm not using this in. 4.95 times 10 to the 5 joules per kilogram. So if we get those, put those in the equation, we can work out what the normalized enthalpy is, and we get a value of 7.66. Anyone remember what it was at what stage we might get transition? What was that normalized enthalpy?
Up to 6, isn't it?
That's right, 6, yeah. So, it is most likely that because this value is greater than 6, so this is your normalized enthalpy here, they say after 6 it becomes likely, and I think with a lot of this we have to deal with it as a likelihood. If you look enough at these graphs with enough variability, they say that that value is 6. So after 6 is most likely being keyhole made. So just to finish off that bit on keyhole melting, and then I'll shut up. So if you follow that type of calculation, we've seen that before in the process map, the simulated process map. Power going on the left-hand side, and laser speed going on the right-hand side. And if we calculate for each of these power laser points, we work out what the normalized enthalpy will be. You can see quite clearly. Low speeds, high power, high likelihood of keyhole melting. High speeds, low power. You won't even be melting, but that normalized enthalpy is down here quite low. So again, even for complicated equations, it actually is quite logical, what you'd expect. So I'm not going to do any more today. We'll go on to next week to going through residual stress and the rest of the process-related defects that we get when we finish up our chapter. I'll see you tomorrow for the facts. Yeah.